Section 25.2 Weather Variables. So air pressure, temperature, and density is what controls the air's behavior, and thus that's what controls the weather. Air pressure is produced by numerous air particles and air molecules crashing into each other all the time. The more air molecules there are, the more collisions, the greater the air pressure. The faster the molecules move, the greater the kinetic energy they have, and thus the greater air pressure. So warmer air has higher pressure than cooler air. Likewise, the more dense the air is, the more air molecules there are, the more collisions there will be, and the greater the pressure. Air will become less dense when it expands, and it becomes more dense when it contracts. Atmospheric pressure, and thereby air pressure, is measured using a barometer. Barometers are generally made from mercury, and what you have is a tube sitting inside of a bowl of liquid, and the atmospheric pressure, the pressure outside, can push down on the liquid, forcing the mercury inside the tube upwards, and you can measure the height of the tube. For standard atmospheric pressure, the height of the tube would be 760 millimeters. So when you add heat to an air mass, the air temperature either increases or the air pressure increases, or both occur. And heat can be added by solar radiation, or by moisture condensation, or by contact with warm ground. Air can lose heat by radiation into space, by evaporation of rain in dry air, or by contact with cold surfaces. However, air can change temperature without the loss or gain of heat, and that change of temperature or pressure without an exchange of heat is what's called an adiabatic process. This occurs when air expands or contracts. Most times this occurs whenever there's no time for heat exchange to occur as the volume is changing, so the air is forced upwards over a mountain very quickly. However, adiabatic processes are not restricted to dry air. As the air cools, it can hold less water, and then water vapor can condense and form a cloud. And so if a mass of air with some amount of dissolved water vapor is forced upwards by a mountain or something like that, that water vapor can condense rapidly and form a cloud. So the way that the air behaves can be thought of in terms of the ideal gas law, where the pressure of the gas is just approximately equal to the density of the gas times the temperature. And the temperature changes occur as a result of the expanding and contracting of the air, not as a result of heat exchange. There's nothing heating the air. It's just because the air is given more space or less space to move around. As air rises up, there's just less air particles, so the air can spread out. And as it spreads out, the temperature changes. Now, assuming near the surface there are very small changes in density, when the pressure goes up, the temperature will go up, and when the pressure goes down, the temperature will go down. Assuming that the ground is around 25 degrees Celsius, for every kilometer of altitude you lose about 10 degrees Celsius of air temperature. So the same parcel of air, as you move it up every kilometer, the temperature will go down by approximately 10 degrees Celsius. If the air is saturated with water vapor, then the difference is only about 6 degrees Celsius. If you force a parcel of air to a lower elevation, it will warm up and then return to its original altitude, and the air parcel remains stable with respect to its environment. It just moves up and down. A similar process can occur if the air is forced upwards. However, if the rising or lowering air stays warmer than its surroundings, then it will not be able to just float back down. If it doesn't cool, it won't be able to move back down to the surface. And so that air would be unstable. And the air around that piece of air helps to determine the stability of that air parcel, whether the air is warmer or cooler near that area. The environmental lapse rate describes how the air outside of that air parcel will change with altitude. In general, you see a decrease of about 6.5 degrees Celsius per kilometer of altitude. However, it can vary from day to day and from place to place. Sometimes cold air can get trapped at lower elevations with warmer air above it, and this is called a temperature inversion. These can occur in the atmosphere as well, where air molecules have a higher temperature in upper levels.